Hey guys, how's everyone doing?
Great, Professor. How was your break?
Busy.
Mine wasn't much of a break either.
Yeah, well, welcome to adult life. Uh,
Will we
well,
be doing chapter 6 from now on?
yeah, so this week we have 3 weeks left, right? And well, let me switch the camera. Yes, we will do chapter 6, but not all of it. We'll just do several sections.
And
Um,
then that will be all for the final then, or will it be one more chapter? Oh,
yeah, yeah,
there we
yeah.
go.
I think we'll just do 6 and kind of end there. It's chapter 7. Like if we had more, maybe you guys want to do chapter 7? We could fit it in if we squeeze a little bit. But I don't think it's not really that essential. I don't think. Yeah, I think like yeah, we'll do chapter 6. Um, and then maybe I guess we could decide on the last week. So like for now the plan is so this week. I think we did 6.1. We'll run through 6.1 a little bit today again, just to review. So we'll try to do like up to 6.4. And we'll have one last quiz. So I'll assign it this week. And I think since so basically we have three things due more. We have one more quiz, we have one more midterm, and we have a final exam. All right, and I know a lot of you guys are asking for extension, so just kind of keep in mind, the quiz 10, you should start doing it this week after we're done. Midterm 3, you can start working on it next week. And then final exam would be for the last week. But I'll make them all due like at the end. So I just kind of, I'm gonna make quiz 10 due December 13th. So I think it's like the last class. And then midterm 3 will be due December 14th. I think that's Thursday. And then final exam, the latest I can make it due is December 15th because I have to kind of over that weekend, I have to grade everything and submit you guys' grades. So, and yeah, I can basically extend everything too, but like no later than December 15th. So kind of keep in mind that you have to try to finish everything up by December 15th. All right. Yeah, but again, so this week we'll do chapter 6. You'll have a quiz on chapter 6. Then next week we'll kind of continue finishing up chapter 6. If we have time and you guys want to do a little bit chapter 7, we can do that, but we can see as we go. And then I'll post I'll work on your midterm 3 this week, so maybe I'll post it this week. But midterm 3 will include kind of all of the sections in chapter 6, so we'll have to kind of do homework here first before you guys do the midterm.
Are
All
we
right.
skipping 6.5 and 6.8?
Um, so we'll see how much time we have. All right, so kind of like important sections are 6.4 and 6.7. So if we have a lot of time, we'll do 6.5 and 6.8. If we're running short on time, like we'll just do 6.5. Or if we're really running short on time, then we'll skip 6.5 too. So those are just applications.
Okay.
But yeah, we'll try and do 6.5. This squares is pretty useful thing, so we'll try and do that. I guess we'll just kind of go and see how much time we have. Right.
And if to study for the final,
Mhm.
would it be best just to study them each of the exams previously?
Yeah, definitely. Like if you do, you should start with just going over all of the quizzes and quiz solutions and all of the exams and all exam solutions. But the only problem with midterm 3 is that, like, if it's due the same time, you're not going to have midterm 3 solutions posted.
Hmm. Would
But
you be able to, if we submit
mhm.
midterm 3 like a week before the 14th, would you be able to privately email us the solutions?
Yeah, that's what I was gonna say. I could do that. Yeah, yeah, definitely. Like so, yeah, like if you have submitted it already, I'll send you a solution. I think that's a good way.
Awesome.
So, and then also, so like the very last week, right? Your exam week. I think we're not going to do anything new, so we'll have. There's two classes there. Right, an exam is due, you have like 2 more days after the classes are over. So this week we'll just do, like, we'll just solve practice problems from the whole semester so you guys can prepare for the final exam. It's kind of what we did for midterm too. Remember, we had one class where we just kind of went over all the topics and did some example problems to prepare for midterm too. So we'll kind of do the same thing here in the last week, but like in relation to the final exam. Well, I mean, and maybe like with more weight on kind of problems from chapter 5 and 6, right? Since it's newer material. That makes sense. So again, like we have 3 weeks left, and I mean, we don't really have that much stuff to cover, just like some sections from chapter 6, and then we'll have plenty of time to just do random practice problems and prepare. All right, but you guys should try to kind of catch up on, like if you're doing online homework, try to catch up on your homework. Again, quizzes. So there's one more quiz. I think quiz 9. Did you guys all do quiz 9? Does anyone need an extension? I think someone was asking for extension on quiz 9. Yeah, I didn't post solutions for quiz 9 yet, so if you didn't do it, you should still try and do that one. Because I think at the end, I think I promised you I'm gonna drop 2 lowest quiz scores, something like that. So if you missed the quiz or did bad on some quizzes, like you have a chance to make up for it. And then also like text me through Canvas if you have some concerns, because I mean if you're missing a few quizzes and you're worried about it, I mean I don't mind giving you like some like optional like quiz 11 or something like that. And then so if you guys want an extra quiz to like make up for some other quizzes. All right, so just like text me about it. That makes sense. Are there any questions on kind of our schedule for the rest of the semester? That's all good. Oh yeah, one more note about the midterm 2 that you guys did. So someone was emailing me. So midterm 2, and it's kind of confusing because I tried to change it. Because midterm 2 is out of 100 points total. Now, but when you're doing your exam, you actually have for some reason I can't, it doesn't let me change it because you guys already took the exam. So overall there is 120 possible points on your midterm 2, because there was like 2 extra credit problems. I mean, there weren't any particular problems, it's just like you have a total of 120 points on that exam, but to get 100% you only need 100 points, and all of those extra points I can add to like midterm 1 or midterm 3. All right. And I think what I'll do, I'm going to add all of your like midterm scores and then divide them by 3, right? So say if you had like midterm 1 and midterm 2, right? And you got like, I don't know, like 80% on midterm 1, and on midterm 2, you got 110%, right? Then I'll just make another grade column where you would have like your kind of average midterm score, right? Where I would just do 80 plus 110, right? So I would have 190 over 2, right? And that would be your kind of overall midterm score, right? So it's not like, I think when you look at Canvas, it tells you your grade out of 120, but it's like, it's actually grade out of, it should be grade out of 100. I'll work on it and try and fix it, but kind of, I tried to fix it for some time and it doesn't let me do it. So I'll just make like another grade column for your midterm, all right? You can just look at your overall points and just consider them as like out of 100 points. If you have more than 100, then you have extra credit points. That makes sense? Yeah. All right. Or I mean, another way you can look at it is like if you got 110 on midterm 2, then this is like 100 for midterm 2, and now your new score for midterm 1 is 90. I like that. Make sense? Yeah. Questions? No? All right. So maybe I'll write an announcement about all of that. All right, well, let's get to, I mean, unless you guys have questions, I can get back to chapter 6. finish this up. So, I mean, we had a lecture on 6.1, right? But I know it was like a whole week ago, so maybe we'll just kind of run through it really quickly to review and then start chapter 6.2, right? So in chapter 6, we're going to be dealing with inner products, all right? And we defined inner product in 6.1. I mean, there's different names for it. There's inner product, there's dot product. Sometimes people call it a scalar product because basically what you get out of this, you multiplying, it's a way to multiply two vectors in order to get a scalar quantity out of it. So the dot product is defined vector u dot vector v, right? They have to be vectors of the same dimension, right? But it's basically a vector multiplication of transpose of the first vector times the second vector. So I mean, really what happens is you basically multiply component by component and add everything, right? This is basically my vector multiplication, right? My row by column rule. Right? So you end up with a scalar. So that's how we defined it. We did some examples how to compute our inner products and dot products. We did some theorems. You know, how do you do algebra with those dot products? And I mean, it wasn't really that complicated. I mean, one thing we showed, like we have commutativity for dot products. So u dot v is the same as v dot u, right? And I mean, you can see all that just from kind of from definition, right? If I have like v transpose here and u here, I would just be multiplying like v1, u1, vn, un, right? But the result is still the same, right? Because multiplication of real numbers is commutative. My dot products would also be commutative, right? So we have commutativity, we have distributive property, right? If I have sum of two vectors and I'm doing dot product with another vector, I can distribute this w. With constants, right, we can factor them out and multiply to any one of the vectors first. I mean, also another thing we had is if I'm doing dot product of vector to itself, the result is always going to be greater or equal to 0, and it will only be 0 if the vector itself is a 0 vector, right? Also, something you can see when you write down the definition, right? If you're doing u dot u, you just end up having sum of squares of components of u, right? Squares are always positive or 0, right? And this sum would only be 0 if each one of the components is 0, right? So that's where this property comes from. Right, so we don't have to reprove all of this, but when we do algebra with dot products, you're basically just using all of those things. All right, we did that. Then we kind of looked at the notion of the lengths of the vector, but in this new notation, right, we know how to compute lengths of vectors in R2, right, by just Pythagorean theorem, right? If I had a vector with components like A and B, I mean, this is just basically lengths of the hypotenuse by Pythagorean theorem. But we can extend this notion to kind of any Rn vector, right? And we just kind of wrote this in this new notation with our dot products, right? We introduced this norm notation, you know, like double absolute value of the vector. Basically describes norm of the vector or the length of the vector, right? And we can define it in terms of dot products as square root of the v dot v. Right? Which basically gives us our familiar Pythagorean formula for length. Right? In practice, when you're trying to show things, like if you wanted to show that v vector of 0 length or something like that, a lot of the times it's kind of easier just to deal with squares of norms or squares of distances, kind of to avoid those ugly square roots. Right? So a lot of the times you will see that people are kind of you're trying to show something about lengths, you kind of just compute square of lengths first. I mean, the reason for that is just because you don't want to deal with square roots, right? You just want to do dot product, and then if you need to take square root, you can take it later. So we did this, our definition, we did some kind of more rules for norms, right? If I have a vector scaled by some scalar c, and I can basically take this out, but I have to put an absolute value on my c, right? Because I mean, this is distance, right? So even if c is negative, it would still be kind of stretching or contracting the vector v based on absolute value of c, right? So if like a C is -3, we'll still be stretching the vector V just in the opposite direction, right? So, I mean, this rule is something you can use without kind of having to prove this all the time, right? Then we define what it is to be a unit vector. So, I mean, unit vector is just vector that has length 1, right? So you can think of your kind of standard basis. Like all of those vectors have length 1, so they're unit vectors. And then if the vector is not a unit vector, so it does not have length of 1, you can easily what's called normalize it, right? You can turn it into a vector of length 1 that points in the same direction, right? And basically for any vector V in Rn, I mean, all you do is like you take that vector and basically just divide it by its length. And this will give you the unit vector in the direction of V, right? So this process is called normalizing. Right, so we did kind of examples last time for it. It's not too bad. We did, okay, it was like some examples here. So we just, so we did this in the previous lecture, we're kind of just running through it to review. So we define the distance in Rn also in terms of our like dot product or norms, right? So if I have two vectors u and v in Rn, then we can express the distance between u and v, right? So the distance between u and v, you can think of it as kind of like the distance between the tips of my two vectors, right? By the length of the vector u minus v, right? And here you can kind of see it better by the picture probably, right? So why is it u minus v? So if you have vector u, right, and vector v, and you want to compute the distance between u and v, geometrically, what is this vector here if I was to draw a vector like from the tip of v to tip of u, right? If this is v, this is minus v. U minus v is u plus minus v, right? By parallelogram rule, so if I would have u and minus v, then my resulting vector would be u minus v over here, right? And this vector is exactly the same as the vector that goes from tip of v to tip of u, right? So the distance between v and u is basically norm of u minus v, or kind of length of the vector u minus v. That makes sense? Yeah, so that's our distance between two vectors. We defined with a formula that we can use. All right, we did some examples again, and like we had some analogy with like R3 and R2, right? And R2, if I'm doing distance between two vectors, I can use Pythagorean theorem, right? I have distance between those two vectors. This distance is my hypotenuse, right? And I have lengths of two sides. Here, length of one side is u1 minus u, actually, I have, yeah, u1 minus v1, and this is u2 minus v2, right? So just squaring length of two sides, taking square root, and this will be the length of my hypotenuse, or the distance between the two vectors. All right, so this formula just gives us a much more general way to compute this, right? It does not have to be R2 where we're using Pythagorean theorem in R2, right? So I mean, basically this is the same as Pythagorean theorem, just extended to all of Rn, right? It doesn't have to be R2 or R3, it could be like R100 if you want to. All right, so we did this. And then we start talking about called orthogonal vectors, right? And again, we're kind of extending all of the kind of familiar concepts from geometry, but to kind of more general spaces, or at least starting with extending it from like R2 to Rn. All right, and in R2, orthogonal vectors, I mean, they're basically vectors that intersect at the right angle, right? They're perpendicular. It's basically a notion of perpendicularity of two vectors extended to Rn, right? And we kind of defined it, again, without using the fact that we're in Rn, and just using our kind of norms and dot products, right? So if I have some two vectors, u and v, right, they're in Rn, how can I geometrically describe that U is perpendicular or orthogonal to V, right? What I can do is I can say, well, if this vector is V and this vector is minus V, I mean, this would be the right angle if this distance here from V to U is the same as the distance from U to minus V, right? So I'm kind of forming this triangle here with equal, two equal sides, right? And then I'm basically using this geometric property as my algebraic statement that I will kind of expand to get some algebraic condition for orthogonality of vectors, right? This distance here is U minus V norm, and this distance here is U minus V norm, right? Lengths. I said those equal. What we did is we kind of expanded this side, right, using our properties. And again, here, look, I'm using square of the norm. Like I said earlier, I mean, sometimes it's just a lot easier to kind of avoid those square roots, right? That's kind of the only reason why you're doing the square here. Right. So we expanded this guy here squared, right? Just kind of using our definitions, right? Norm squared is basically the dot product of vector to itself, right? Then we use distributive properties. We use commutative properties to kind of rewrite this whole expression as basically this what looks like a quadratic here, right? I have norm of U squared plus 2U dot V plus norm of V squared. And then we did this with the other side too, and then compared the two. They have to be equal in order for U and V to be perpendicular or orthogonal. And if they're equal, I mean, this is the same, this is the same. So really I need to have 2U dot V equals to minus 2U dot V, right? So for orthogonality, we got this important condition that two vectors are going to be orthogonal if their dot product, or their scalar product, is equal to 0, right? So, and it's a very easy condition to check, right? You just have to take the dot product of two vectors. If it's 0, then those two vectors are orthogonal or perpendicular. But that kind of basically defined our orthogonality condition by using the dot product, right? We talked about, zero vector is always a little bit different, right? Remember with the linearly independent sets, having zero vector, what makes that linearly dependent, and then also zero vector here, because it has to fit into this definition also, right? If I dot zero vector with any other vector, it's always going to be 0. So we're kind of considering our zero vector to be orthogonal to every vector in Rn. So it's one vector that's orthogonal to everything, just because it kind of fits that definition. And there's other conditions too you can check, depending on what you're doing. I mean, this is the easiest one to check for orthogonality, but there are other formulas. Like if you have two vectors U and V, they are orthogonal if and only if the norm squared, the norm of the sum squared equals to the sum of the norms squared. Right, and this formula comes from our derivation here, basically, when we were expanding this, right? It came from this, right? Because if I expanded U plus V squared, I would end up with norm of U squared, norm of V squared plus 2U dot V, right? This is 0 if and only if the vectors are orthogonal, so this formula is true if and only if U and V are orthogonal. All right, so just kind of depending on what you're doing, all right, which could be a nice formula to use. All right, but I mean, most of the time you're just using U dot V is 0 for orthogonality. And so we talked about orthogonal components. I guess have any questions so far? Yes.
No, it's all clear and perfect.
Yeah, just kind of definitions mostly. So then we talked about orthogonal components, right? So if I have a vector Z here, say I have like maybe a plane and the vector Z, right? That vector is orthogonal to every vector that lies on that plane, right? So we can say that that vector z is orthogonal to W, which is a plane, right? And we also define an orthogonal complement, right? The set of all vectors orthogonal to some subspace W is called the orthogonal complement of W, right? And we have kind of this sign for it, like upside down T, right? So W perpendicular or W perp or orthogonal complement of W is basically a collection of all vectors that are orthogonal to W, right? So I'm gonna one example to kind of get a grasp on it we had was, if I have the origin and I have a subspace, say it's a plane through the origin, right? So if I have any vector W that lies on that plane, if I wanted to look at, I mean, what is my orthogonal complement of W, right? What are all the vectors that are going to be orthogonal to this vector W, all other vectors in that plane, right? And those vectors would basically be all of the vectors that lie on the line, but also through the origin. Remember, we have to kind of like fix ourselves to the origin here, right? And the line that is kind of perpendicular to this subspace W, which is the plane, right? So, I mean, another way to look at it, you can kind of define a line in a plane with two vectors. So vector Z lies on a line, and vector W is some vector on this plane. So if those two vectors are perpendicular, then I'm going to have that this line defined by vector Z and this plane defined by kind of like all of the vectors W that lies here that are orthogonal complements, right? So line is the orthogonal complement of the plane, and the plane is orthogonal complement of the line. Does that make sense? Right. All right. So we have some little theorems too, which we proved last time, right? If I have a vector x in the orthogonal complement of some subspace W, not this would be true if and only if x is orthogonal to every vector in a set that spans W, right? So really, like all we have to do is just latch on to our kind of vectors that span our space and kind of test them for being orthogonal to X that is an orthogonal complement, right? So you don't have to check every vector, you just have to check the vectors that span that subspace, right? And we also showed that orthogonal complement is always going to be a subspace, right? So if W is subspace, orthogonal complement is also going to be subspace, right? We're kind of always trying to deal with subspaces, right? I mean, how do we show that something is a subspace? I mean, we have to show those three conditions, like closure under scalar multiplication, closure under addition, and that the zero element is in that space. All right. So we did that. And then we kind of finished with the theorem, where we actually looked back a little bit at our row spaces and column spaces. So we have a theorem that says that orthogonal complement of row space of the matrix A is exactly the null space of A. And orthogonal complement of the column space of A is the null space of A transpose. Right? So it kind of looks like how did we get this? Right? But it's actually not that hard if you kind of write out your kind of matrix multiplication here. So just remember, how do we define null space of A, right? Null space of A are all of the x's in Rn or Rm, whatever we're dealing with, such that my Ax equals to 0. Right, so those are all of our solutions of the homogeneous equation, right? That's my null space of A. So if I'm looking at the row space of A, I can just write down my multiplication A times the vector X, right? I have basically rows of A multiplied by X, right? I have first row of A multiplied by column X, right? Because remember, it's our row by column rule, right? I have first row by X, second row by X, third row by X, and then mth row by X, right? So, but if I'm looking how I'm multiplying it when I'm doing row by column, right? I'm multiplying, right? First components plus second components plus third, right? All the way. And basically each one of the rows in my resulting vector, I mean, it's going to be numbers, right? Is really defined exactly as my dot product, right? I have sum of multiplication of components, right? So this multiplication of first row by x is really equivalent to taking a dot product of the first row of matrix A with my vector x. When I go to the second component, again, it's the same thing. I have row by column, right? I have second row multiplied by x. So multiplying component by component and adding everything up. So it's equivalent to doing a dot product, right? Second row of A, dot product with X. Right, and all the way to the very end. So if I have like M rows, I have M components in this resulting vector. So and the last one is also a dot product. Right, and once you have this, I mean, this becomes pretty apparent, right? Because if X is in a null space of A, right, when we're proving this, we're basically showing kind of this is a subset of that, and this is a subset of that, right? And if null space is a subspace of orthogonal complement of row space of A, and orthogonal complement of row space of A is a subset of null space, then they have to be equal, right? Because they're subsets of each other, right? So you kind of start with, okay, if X is in a null space, if X is here, then, I mean, I know that X is a solution of the homogeneous problem, right? By definition of null space. Right, so that basically means that this column vector here with a bunch of dot products of rows of A and X equals to a zero vector. So each one of those dot products equals to 0. And if each one of those dot products equals to 0, orthogonality condition, right? If dot product is 0, then those two vectors are orthogonal. So that means that X is orthogonal to all rows of A. And if X is orthogonal to rows of A, then that means that X belongs to the orthogonal complement of the row space of A, right? Because those rows of A basically span my row space, right? And if X is orthogonal to all of the vectors in a span, then it's orthogonal to the whole subspace, right? So then X belongs to orthogonal complement row of A. That makes sense? Yeah. And then in the opposite direction, if I assume that X belongs to orthogonal complement of row space of A, again, we're kind of just using this kind of this way of writing A times X, right? We know that X is orthogonal to each row of A because it's an orthogonal complement of row space, right? And again, by this, if X is orthogonal to each row, each one of those guys is going to be equal to 0. So then AX will be equal to 0, meaning that X belongs to the null space of A. Yeah. So we showed this. And the second one is really easy, right? Because if this is true for any matrix A, if I just replace A with A transpose here and here, right? I would get row A transpose, null A transpose, but then row space of A transpose is the column space of A. So that's basically how you get the second relation here. So I mean, you can use this in a lot of ways. We did kind of like the last example we did last time is, right, if I have a subspace of Rn, W, then orthogonal complement W is also a subspace. We showed that already. But not only that, if we're dealing with Rn, the sum of dimensions of W and its orthogonal complement is going to be always equal to n, right? So they will always add up. So like if I'm dealing with Rn, dimension of W is like P, then dimension of the orthogonal complement will have to cover everything else up to n. So that would be n minus P, right? And we've seen something like this before, right? Remember the rank nullity theorem, rank plus nullity equals to n. So this is actually all related, right? If I had a subspace W with some basis, for W, so W has dimension P, so it has P elements in the basis. You can actually use the previous theorem very easily here. Remember, we're dealing with like dot products and the rows. What you can do is you can basically use that basis and form a matrix A P by N, right? P rows, each row is basically transposes of each one of my basis vectors. So I'm taking basis vectors for W and using them as rows in my matrix A, right? So then my space, subspace W is really just the same as the row space of this matrix A, right? My basis vectors are rows, right? So then dimension of the row space of A will be equal to dimension of W equal to rank of A, right? And then my orthogonal complement of W is going to be null space from the theorem we just did, right? Dimension of the null space and rank, I can basically rewrite this as rank nullity theorem to show that part. Right. So that's basically all we have for 6.1. You guys have any questions on 6.1? No, straightforward. All right, so we'll do 6.2. All right, so let's do a little bit more. So we'll go and look more at kind of this orthogonality condition and look at what's called orthogonal sets. Right, so what are, I mean, we know what linearly independent sets are. So now we'll kind of introduce another condition on our sets of vectors, and it's an orthogonality condition. So the definition is the set of vectors, so all those vectors are in Rn. We're going to call this an orthogonal set if each pair of distinct vectors from the set is orthogonal. So if I take any any two vectors from this set, their dot product will be equal to 0. That's our orthogonality condition, right? So, and that should be true for any two vectors I pick in that set, right? So, I mean, generally, if you want to show that something is an orthogonal set, you do have to look at, what are all possible kind of combinations of two vectors. But you can just start with first one, like U1 and U2, U1 and U3, right? U1 and U2, U1 and U3. Take dot products, right? Using our definition, have U1 dot U2, 0. Okay, U1 and U2 are orthogonal. U1 and U3, again, use definition of dot product, compute it, equal to 0. Yeah, U1 and U3 are orthogonal. Then go to the next one, U2, right? Do I need to do U2 and U1? No, because I already did U1 and U2, right? And dot product is commutative, so right, U1 dot U2 is the same as U2 dot U1, right? So just go to the next one and do the one that you didn't do it with yet, which would be the next one, U3. So U2 and U3 dot product equals to 0. And I mean, that's it. I mean, I can't really take any more pairs that I don't have here already. All right, so because any pair of vectors I pick, well, distinct vectors from this set, has 0 dot products, which means that all of those vectors are orthogonal. So this makes it an orthogonal set of vectors. Using this analytic condition. So we have a theorem. It's actually a really powerful theorem, right? If I have a set of vectors, say p vectors, and it is an orthogonal set, I mean, also I'm assuming that they're non-zero vectors, right? I don't want to have any zeros in here. They're all non-zero vectors. But I know that they're all orthogonal. So any two pairs of vectors from the set dot product will be equal to 0. Then S will necessarily also be linearly independent, and hence is a basis for a subspace spanned by S. So basically, this could be another condition we can use to show that vectors are linearly independent. Right? If the set of vectors is orthogonal, then they definitely will also be linearly independent. But it doesn't particularly work the other way around. Just because they're linearly independent I mean, we're not proving here that that means they're orthogonal. We're just showing that if they're orthogonal, they have to be linearly independent. It doesn't work the other way. But to show this, I mean, I'm assuming they're all orthogonal, right? To show linear independence, vectors are linearly independent if when I form linear combination of all those vectors set it equal to 0, then necessarily all scalars have to be 0. All right, then they're linearly independent. So I start with my linear dependence relation. And since we're dealing with orthogonality, I have to use my dot product somehow. So what if I just take dot product with vector u1 both sides of this? So 0 dot u1 and all of this dot u1, kind of using my distributive property, right? I can distribute this dot product and I end up with c1 u1 dot u1, c2 u2 dot u2, right, all the way to cp up dot u1. So everything is dotted with u1. But now because the set is orthogonal, all of those dot products, right, u2 dot u1, u3 dot u1, all the way to up dot u1, they're all going to be 0 because vectors are orthogonal, except for the case when I'm doing u1 dot u1. Because remember, the dot product is only going to be equal to 0 if the vector itself is 0. And we don't have any 0 vectors here. So all that stuff vanishes, and all I have left, right, 0 dot any vector is 0. And all I have left is c1 u1 dot u1, which is kind of norm of u1 squared. Right. So because my vector u1 is not 0, and this equals to 0, I mean, I must necessarily have that this constant c1 is 0, right? And if you keep repeating this, so now if I dotted this with u2, u3, u4, I will have the same thing, right? If I dotted it with u2, everything would be 0 except for c2 u2 dot u2, right? And then I would need to have c2 equals to 0. So if you repeat this for each one of those vectors, you're basically getting that all of your constants must be equal to 0, which means that my set is also going to be linearly independent. So again, the point here is that if I have an orthogonal set of vectors in Rn, this orthogonality condition necessarily implies that it will also be linearly independent, right? And if we have a linearly independent set of vectors, and we take the span of those vectors, I mean, basically those vectors are a basis for a subspace spanned by them. So we can use kind of orthogonality as instead of the linear independence. Any questions? Not any more definitions. So an orthogonal basis for a subspace W of Rn. Once again, it's basically a basis for W, right? Any vector in W can be expressed as linear combination of those vectors. But not only that, it's also an orthogonal set, right? So they're basically basis vectors that are also orthogonal. And why do we need those orthogonal bases? I mean, they actually make it a little bit easier to compute the weights when you're trying to get your kind of express some vector y and w as a linear combination of those basis vectors, right? If I didn't have an orthogonal set of basis vectors, I mean, how do you find all your weights? You have to write down the linear system, right? Do your like row reduction algorithm, and like it's not super short, right? So you always have to kind of go to linear systems to solve for weights. If your basis is orthogonal, however, it's a little bit easier because we can actually get nice formulas for the weights themselves. We don't have to write the linear system. All right, so in the formulas for those weights associated with orthogonal basis is given by like this y. So we'll derive this in a second. Get so my weights are given to me as y dot uj, uj dot uj for each one of the weights, right? But you can see how we get this. You're gonna get this very similarly to how we did the previous theorem, right? So if I have an orthogonal basis for some space W, right? And Y is any vector in the subspace W. All right, so Y can be represented as linear combination of those basis vectors, but what I want to know is like, what are my C's, C1 through CP? To find C1, do dot product with U1, right? So Y dot U1, on the right-hand side, I distribute U1, right? And then same principle as before, right? Because those vectors are orthogonal, U2 dot U1 all the way to UP dot U1, they're all those dot products are 0. So the only thing that survives is U1 dot U1, right? And we basically have a formula for computing C1, right? C1 is Y dot U1, U1 dot U1, right? You can do this for any J in your list from 1 to P, right? Kind of same idea, right? If I dot with UJ, the only term that will survive on the right is basically CJ, UJ dot UJ, right? Everything else is 0 bar orthogonality. So that basically gives us the formula for computing weights in this linear combination, right? So all you have to do is just do dot products with your basis vectors and like the norm squared of the basis vector, right? You can also write this as CJ is Y dot UJ. And sometimes people write like norm UJ squared. So, right, because UJ dot UJ. So basically just gives us the formula for computing weights. So you don't have to do kind of solve linear system to find your CIs. That makes sense? It's kind of like the main usefulness of kind of having orthogonal bases. All right, so we can do some examples here. So suppose I have U1, U2, and U3, those three vectors. So when I'm taking set of those three vectors, and I know that I already checked that it's an orthogonal basis for R3, right? So if I just check orthogonality, right? If U1 dot U2 0, U1 dot U3 0, U2 dot U3 0, they're all orthogonal, therefore they're linearly independent. Three linearly independent vectors in R3 form a basis. They're orthogonal, so it's an orthogonal basis. All right. So we're not proving that here. We know it's an orthogonal basis, but if I want to express this vector y in R3 as the linear combination of those three orthogonal bases, right? Basically, it's the problem of finding those weights C1, C2, and C3. All right. If I did it with methods we did before, what would I do? Right? I would put those in the matrix, right? I would have this matrix A consisting of those three rows, three columns, right? Times X equals to Y. I have to kind of do row reduction to solve for my C1, C2, C3. Right? I mean, you can still do this here, but it's a little bit easier to do it this way without the matrix. Because my basis is orthogonal, I can use those formulas for computing C1, C2, and C3. All right, for C1 is Y dotted with U1 divided by norm U1 squared, right? So if you do the dot product, right, Y dot U1, 6 times 3 plus 1 times 1 plus minus 8 times 1, right, be 11. And then U1 dot U1 also, right, 3 squared plus 1 squared plus 1 squared of 11. And basically applying those formulas in all three cases, we're getting our values for our weights. We can just put in the formula, and here we go. We have the linear combination of those orthogonal basis vectors that give us our vector y that we wanted. So it's just a little bit neater to deal with than when you have to deal with linear systems, when you have those orthogonal bases. Right? You have like nice formulas in terms of those dot products. That makes sense? Yeah. Questions? All right. Next one. So next notion we have is it's called an orthogonal projection. So, I mean, if you guys took any physics, I mean, you've dealt with this before. Like when you have those force problems, you have to decompose like the force vector into a component like parallel to line of motion and perpendicular to line of motion. This is basically what this is, but kind of more general. All right, so what we're doing here is, if I have some vector u, right, that kind of like defines some particular direction of interest for me. So like if I'm dealing with, I don't know, maybe some like carts on the incline. I remember in physics, like you're applying like force this way, you have like gravitational acceleration this way, right? So you have some direction that are important to you, right? If you wanted to calculate like static friction, this direction parallel to the slope is important. If you want, the dynamic friction, if you want to do like static friction, then you have to look at the perpendicular component, right? So depending on geometry of the problem, like some of those directions could be important to you, right? Also like direction of the gravity and things like that. So this vector u is basically this fixed vector that kind of defines like a coordinate system or important direction like related to your problem. Now, so u is a fixed vector in Rn. And then if y is any other vector in Rn, right? What we sometimes may want to do is decompose this vector y into the sum of two vectors, where one of the vectors is going to be in this direction of interest u. So this vector is some scalar multiple of u. You can say this vector belongs to the span of u. And then the question is, what is the other vector that I will have? And this other vector that I want to have the orthogonal vector to u. So I'm basically decomposing it into like orthogonal components, right? One component of vector y in direction of u, and another component vector y in the direction perpendicular to u, right? Again, if you guys did, I'm sure all of you did some physics, right? It's when you just think of decomposing force vectors into orthogonal components. It's the same thing, just a little bit more general here, because we could do it not just actually for vectors, we could do it for any vector space, like we could do it for functions and things like that also, right? But we need to get some formulas down here, and we're basically just kind of looking at our setup. I mean, what do I want? I want to have any vector y in Rn decomposed into kind of some of those two components, right? One vector that's a multiple of u, so that in the direction of u, and the other vector that is orthogonal to u, right? All right, so what do I find first? I mean, I know since this is orthogonal to u, my vector z, if I rewrite this as my general vector y minus component of y in direction u, so z is y minus y hat, right? And then because y hat is just a multiple of u, this is y minus alpha u. And we know that this vector z is orthogonal to u. So by orthogonality condition is, if they're orthogonal, then u dot z has to be equal to 0, right? So u dot z equals to this or this, right? U dot y minus y hat, or u dot y minus alpha u equal to 0. All right, so we're gonna use this condition, u dot y minus alpha u equals to 0, distribute u, right? So I have u dot y minus alpha u dot u, right? And we're getting the relationship here, right? U dot y equals to alpha u dot u, which I can solve for this alpha, right? So basically first solving for, I mean, what would this be? What is my component of y in the direction of u? So solving for alpha, I have u dot y divided by u dot u. And remember, unless u is 0, dot product of u dot u is not going to be equal to 0. So I can divide by it, right? So alpha is u dot y divided by u dot u. And then substituting this into my expression for y hat, I have my alpha. So y hat is u dot y divided by u dot u times my vector u, right? Because this is a vector. My dot products are scalar. So this is just the value of my scalar alpha. Right? So we're getting the formula for y hat. And we have a name for this, right? So this y hat is going to be called orthogonal projection of my vector y onto u. Right? So if I have vector y here, and I have my vector u here. So, I mean, you can think of like a line running in a direction of u, right? You can look at this line as it's a span of my vector u, right? I mean, line is a subspace of Rn, spanned by one vector. So what I'm doing here, I'm basically looking at, well, if I have my vector y, and I just fucking go orthogonally down to the line defined by u. What is this component here along this vector u of my y? And kind of like if I was living on this line and I was just looking up, how does my vector y looks like? I'm just taking like projection. Right. So, and we derived the formula on the previous page, right? This was our alpha times u. I got the formula for alpha. And kind of the new notation we're using. So I'm using L, right? I mean, I could use u here also, but I'm basically saying that my y hat is the projection of the vector y onto the line L defined by this vector u. Right? I mean, you can put vector u here also. And just, I mean, it depends on the problem. Like you could also say projection of y onto vector u. I mean, it basically just specifies like, what are you projecting onto? And we have the formula. So this is my orthogonal projection of y onto L, a line determined by vector u. That makes sense? Yeah. So then what is this z? I mean, z is going to be the component of y orthogonal to u because this is how we defined our y hat. We defined it so that y minus y hat, which equals to z, is orthogonal to u. So now using this formula for y hat, I will be sure that z will be orthogonal to u. All right. So how do we find z? Go by example, right? I have two vectors. So y is just that any vector in Rn, and u is the vector that defines that kind of direction of interest for us. So u is this fixed vector. So if I want to find an orthogonal projection of y onto u, and I want to write y as the sum of two orthogonal vectors, one in the span of u, right? So this is my y hat, and one orthogonal to u, so this is my z, right? All right, so I have my vector y, I have my vector u, so I can kind of imagine there's a line going in the direction of u here. And I'm basically trying to project this vector y onto this line, right? So kind of if you drop the 90-degree angle to the line, I mean, this would be the vector in the direction of that I need, right? So, okay, my line is spine of vector u. I have a formula for the projection of vector y onto the line defined by u, right? I have y dot u times u. This is my projection of y onto L. If I get my dot products, right, I have y, I have u, I can compute dot products, right? Y dot u, 7 times 4 plus 6 times 2. Right? U dot u, 4 squared plus 2 squared. Right? I get my constant, right? 40 over 20. I have my vector u, 4 and 2. So I'm basically obtaining my y hat, right? Vector 8 and 2 is orthogonal projection of y onto u. So graphically, this would be the vector that goes from 0 all the way to this point where I'm dropping this line from y at the 90-degree angle to the line L. All right, so this would be my vector y hat. All right. So, okay, but how do you find my z? Well, my z is basically the other vector that I need to in order to complete my y, right? So if this is my vector y, I have y hat plus z, right? But it's easier to compute z just by using what I already have, right? Because my y equals to y hat plus z, so then z would be equal to y minus y hat. I just have to subtract this orthogonal projection from the vector that I initially had, 7 and 6. All right, and that's it. And that would give me my orthogonal z component. All right, so I'm doing my y minus component in the direction of u. And what's left is going to be my y minus y hat. All right, if I put this in an origin, but remember, vectors are not necessarily fixed in space. I mean, it's just direction and length. All right, so this is the same vector as if I put it over here. So, okay, and we basically did this. We decomposed our vector y into component that is parallel to u, and then component that is perpendicular to the vector u. All right, so I kind of decomposed it into y hat plus z that is perpendicular to u. So y hat plus z is y. Make sense? Yeah. So I mean, another way, another type of problem that kind of does the same thing, but maybe a little bit confusing at first. Sometimes you might want to compute the distance from some point, distance from vector y to the line through u, right? So if I have a vector y and I have some line defined by the vector u, so I may be asked to compute the distance from like the points defined by y to the line. So I mean, what is the distance from the line to the point? I mean, usually you look at it as like, what is the shortest distance from this point to the line? And what is the shortest distance? Is it from here to here, from here to here? I mean, the shortest distance would be exactly if I'm going to the line at the right angle, right? So basically the distance from this point to the line is going to be the magnitude of this vector here, or the length of this vector here. And this vector here is exactly my component that's orthogonal to u, component of y orthogonal to u. So we can again use this kind of orthogonal projection, right? Get this vector and then just take the magnitude of that vector. All right, so for that vector y, I have my projection on u. I have the formula for it. So you always have to start with getting your projection first. And then once you have the projection, you basically get your orthogonal component by subtracting your projection from the vector that you had. So projection of y onto line defined by u using formula, right? Y dot u, u dot u times u. Right, you guys know how to do dot products now. So basically compute, okay, it's going to be 2.4 and 1.8. Right, 2.4, 1.8 is my component of y that's parallel to u, right? And then my component that's orthogonal is just going to be my original vector y minus its projection onto the line. So I get 0.6 minus 0.8, right? So since this is this vector here, to get this distance from the point to the line, all I have to do is just take the length of that vector, right? So taking the length, this is square root of the dot product, right? So I'm basically computing the length of that vector, right? It ends up being 1. So my distance from y to the line through u is going to be equal to 1. That makes sense, guys? But whenever you like have those problems, like if I have a line and I have a point, if the problem is like find the distance from the point to the line, you always assume that it's going to be the shortest distance from point to line. Distance from point to line would be the shortest distance, and that shortest distance is when you go at the line at a 90-degree angle. That makes sense? Questions? No questions? All right. A little bit more here. All right, so I mean, so far, what did we do, right? So we looked at orthogonal basis for some subspace of Rn, right? And if I do have an orthogonal basis, right, all of those vectors are orthogonal with each other if I take different pairs, then if I have any vector y and w, and I'm expressing that y as a linear combination of my orthogonal basis vectors, I can actually get the weight by using the formula, right? So Cj's will be equal to y dot uj, j dot uj, right, for each j. I have nice formulas here, right? But since we talked about orthogonal projections a little bit here, what does those terms look a lot like the formula we had just over here for orthogonal projections, right? So my projection of vector y onto the line defined by u was y dot u dot u times u, right? And over here, when we're getting weights, I mean, this looks very, very similar, right? And I have y dot u dot u, right? And I'm multiplying it by corresponding u. So, I mean, it's pretty much exactly the same as the formula for the projection, right? So basically my terms, Cj, Uj, are orthogonal projections onto the one-dimensional subspaces spanned by basis vectors Uj. All right, so each one of those Cj vector Uj is basically one of those orthogonal projections on to each one of those orthogonal basis vectors. All right, so in other words, you can basically look at it as if I take each one of those basis vectors, the span of each one of them separately is going to be a line, right? So L1 is the span of U1, L2 is span of U2, right? Lj is the span of Uj, and so on. All right, so when I'm looking at my formula for computing weights, right, if I write everything down with the formula, y is, right, this is my C1 times U1, Cj times Uj, Cp times Up. I mean, those are exactly formulas for the projections of my vector y onto the lines defined by my basis vectors, right? So my y is really just the sum of projections, y to L1, y to L2, y to Lj, y to Lp, right? Or in our previous notation of our y hats were, right, orthogonal components in direction u, right? So I'm basically decomposing my vector y and w into its projections onto all of those basis vectors, right? So it's just y1 hat, y2 hat, yj, all the way to yp hat. Does that make sense? Right, which is kind of very nice and organized now. Right, I don't have to write linear systems. I can just basically decompose everything into those like projections onto the orthogonal components, onto my orthogonal basis vectors. Right. That makes sense? So I can even like kind of have a picture for two-dimensional case, right? So in R2, so if I had a vector y, right? I mean, what is my y1 and y2 hat? Like if I take y and take projection of y onto direction u1. So if I have two directions, u1 and u2, and u1 and u2 form orthogonal bases. And so I have u1 and u2 orthogonal bases. So in R2, it's pretty easy. I mean, that means they're basically perpendicular vectors, right? I have a right angle here between line L1 and L2. So y1 hat is projection of y onto line L1, right? So it's basically taking a component of y in the direction L1, right? So I'm kind of going at the right angle here to L1, right? So this is my projection. And then y2 is my projection of y onto the line defined by u2. I'm going to go in that direction here. That makes sense? Yeah. Alright, and I can kind of write the formula for it, right? My vector y naught 2 is y1 plus y2, or in terms of formulas, right? I have kind of my weights defined here by those dot products, right? So this is my projection of y onto, well, you can say L1, you can write like U1 in the subscript here also if you want to. Right, projection U2 y, right, or projection L1 y, or projection L2 y. That makes sense? Yeah. Everyone's good. Let's do it. And one other thing we can do is, so orthonormal sets, right? We have a little bit more, right? So, I mean, sets could be linearly independent, they can be orthogonal, right? They can also be orthonormal. So what is an orthonormal set? Well, it's just a set of vectors that is orthogonal, but on top of that, it also just consists of only unit vectors, right? So, I mean, one kind of easy example is my standard basis, right? So my standard basis are all vectors if I have R1 or R2 or even R3, right? My standard basis would be vectors 1, 0, 0, right? 0, 1, 0, and 0, 0, 1. And this is my E1, E2, and E3. Right? So it's one basic example of an orthonormal set of vectors, right? Because if you look at your axes, I mean, you know that your coordinate axes are orthogonal, right? And your basis vectors are just unit vectors that point along the axis. So they are orthogonal to each other, and they're also unit vectors. E1, E2, and E3. So this is one example of an orthonormal set. But I mean, it doesn't have to be those guys necessarily. So I could have like another example. I have those three vectors here. So I mean, the only thing is once you start normalizing vectors, you do end up having a lot of like those ugly square roots and denominators. But I mean, that the square roots come from basically dividing by the length of the vectors. And when you compute length, you get that square root there. So a lot of them will have square roots. So I mean, we didn't finish definition, right? So if I do have a subspace defined by this orthonormal set, this set is going to be an orthonormal basis. I mean, why does it necessarily it's going to be a basis? Well, remember, if my set is orthogonal, it necessarily is going to be linearly independent, right? Orthogonal implies linearly independent. So if I have a set of linearly independent vectors, that's SPAN, W, linear independence give me that it's going to be a basis, right? So it's going to be an orthonormal basis for W, right? Normal because those vectors have length 1, right? And basis because they're linearly independent because they are orthogonal, right? So and if you want to check, right, if you say I have those three vectors and I want to check that those vectors are going to be an orthonormal basis, right? I mean, first thing I can check is, well, are they is this an orthogonal set, right? It's going to be an orthogonal set if kind of all of the different pairs of vectors dot products equal to 0. So, right, v1 dot v2, v1 dot v3, v2 dot v3. You have to check those dot products, right? So we can just do v1 dot v2, right? This times this plus this times that plus this times that, right? My dot product ends up being equal to 0. And if you do the other two, they're also going to be equal to 0, right? So checking those conditions, that's all of the different pairs of vectors dot products are 0, that is orthogonal. So V1, V2, V3 is orthogonal. Orthogonal implies linearly independent, right? And if I have 3 linearly independent vectors in R3, I don't have to check that they span R3, right? Remember our like basis theorems, right? If I know the dimension of my space, R3 has dimension 3, I know that the basis will have 3 linearly independent vectors in it that span the space. And if I have 3 linearly independent vectors in a space of dimension 3, I know that they will span R3, right? By those basis theorem. So it is going to be a basis, right? So, but again, you have to kind of go like, like once you show that the set is orthogonal, right? You conclude that they're linearly independent, but whether it's a basis for whatever space you're given, I mean, you have to check, right? So if this was like R4 or something, and I had more components here, it's not going to span R4. I only have 3 vectors, right? But the fact here that dimension of the space is 3 and I have 3 vectors, they're going to be a basis because they will span it, right? And then the only other thing, the next thing to check, right? So is this in orthonormal basis? For orthonormal, I have to check if all of those guys are going to be unit vectors, right? So again, you just kind of look at all your vectors. What is the length of V1, right? And again, here it's easier to, I mean, why deal with square roots? If square of a number is 1, then the number is going to be 1, right? It's positive number, right? So just check your squares of norms, right? V1 squared is just V1 dot V1, V2 squared, V2 dot V2, V3 squared, V3 dot V3, right? And so on. So if you check all of those, they are all going to be equal to 1, right? So my V1, V2, V3 are unit vectors, right? And they are orthogonal, they're unit vectors. I know that they span R3. So my set V1, V2, V3 is going to be another example of an orthonormal basis for R3. Does that make sense? Yeah. So I guess that's pretty much it for that chapter. Now I should start we will leave the next one for next time. All right, do you guys have any questions? Any questions? You gotta have some questions. No? Not at all?
I think I'm good.
Yeah. All right, so I mean, I think we'll stop here for that. I don't want to rush the next chapter, so I think we'll do. Yeah, I'll do other topics next time. We'll stop here, but we have, so it was 6.2, but it's 6.1, 6.2. So next time we'll do 6.3, 6.4. And I think your quiz, oh, I didn't write your quiz yet, so I'll do it today, maybe. I'll be able to tell you more. But I'll post this today. All right, but with midterms and everything, everyone's good? Yeah. We are here right now. So we're doing 6.3, 6.4 next time. And quiz 10. And then quiz 9, did everyone do your quiz 9?
Yes, I finished it already.
Not too bad.
No,
Do you
it
guys,
was not
do you guys
all.
want more quizzes? Or, like 10, one more. Yeah, like if you want, like look through your quiz scores, right? Keeping in mind, I'll drop 2 lowest scores. Like if you really feel like you need another quiz, like try to email me as soon as possible so I have time to maybe put up like another like quiz 11 or something like that. All right. Then we'll do this, but yeah, I'll do quiz 10 today. Start working on your midterm 3 and catch up on your on grading things. Yeah, but I mean, any questions, any suggestions? I mean, how are did you guys like how are the midterms going? Do you feel like you need more time or like more practice problems?
I think it went pretty well. The first one was a little different because it was different, but the second one was pretty good and easy to do as long as I studied.
Yeah, I think we'll just do basically the same thing as last time for midterm two. I mean, I think like last week we'll just do like review and just do a bunch of practice problems for everything. So I mean, basically you could just like look through your review notes to prepare for it. I think, yeah, and then online homework. All right. Well, no one has no more questions. Yes, no.
No, everything makes sense unless anyone else has questions.
Mm. Well, if you guys are all good, I guess we're done for today. I'll see you next time.
Yeah. Thank you so much, Professor.
Yeah, no problem. Yeah, see you guys next time.